Good evening. As the world outside grows quiet, let us journey together to a place of profound silence and ultimate mystery. We are traveling to the very edge of reality, to where the laws of physics break down and even light itself cannot escape. Close your eyes, breathe, and let your mind drift as we unveil the secrets of the universe's most enigmatic creations. This is 100 Facts About Black Holes, Story Before Sleep. Part 1. The Fundamentals of a Cosmic Giant. Fact 1. The Heart of Gravity's Empire. A black hole, despite its name, is not a hole in the sense of an empty void or a portal to another dimension. It is, in fact, the most crowded place in the universe. It is a region of space-time where an immense amount of matter has been compressed into an astonishingly small area, creating a gravitational field so powerful that it becomes the undisputed ruler of its domain. To picture this, imagine a star many times more massive than our Sun reaching the end of its life. Its nuclear fuel exhausted, it can no longer support its own weight, and it collapses under its own colossal gravity. This collapse is so violent and complete that the star crushes itself down into a point of infinite density called a singularity. This singularity is the true heart of the black hole. Its gravitational pull is so extreme that it warps the fabric of space-time around it into a deep, inescapable well. The edge of this well is called the event horizon, the point of no return. Anything that crosses this boundary, be it a planet, a star, or a beam of light, is captured forever. It's not sucked in as a vacuum cleaner would. Rather, it follows the curved paths of space-time that all now lead to the singularity. So, when we gaze upon a black hole's silhouette against the stars, we are not seeing nothingness. We are witnessing the shadow of an object so dense and so powerful that it has bent reality around itself, a silent, perfect sphere testifying to the ultimate power of gravity. Fact 2. The event horizon, a one-way door. The event horizon is perhaps the most defining feature of a black hole. It is not a physical surface made of matter, but an invisible boundary in space-time, a threshold from which there is no return. The term itself refers to the fact that any event happening inside this boundary can never be observed from the outside, as no information, not even light, can escape to carry news of it. The size of the event horizon, known as the Schwarzschild radius, depends directly on the black hole's mass. For a black hole with the mass of our Sun, this radius would be just under 3 kilometers. For a supermassive black hole containing millions of suns, it could span the size of our solar system. Crossing the event horizon would be a deceptively gentle experience for a traveler, at least for a large black hole. There is no wall to crash into, no sign to mark the passage. One moment you are in the observable universe, and the next you have crossed a line that seals your fate. From that point on, your future contains only one possible direction of travel: inward, toward the singularity. To an outside observer, you would appear to slow down as you approach the horizon, becoming redder and dimmer until you seem to freeze in time, fading away into nothingness over an infinite amount of time, a ghostly echo on the edge of forever. Fact 3. The singularity, where physics ends. At the very center of every black hole lies a concept that continues to challenge the limits of human understanding: the singularity. According to Einstein's theory of general relativity, the singularity is a point of zero volume and infinite density. It is the final destination for all matter that crosses the event horizon, a place where the entire mass of a collapsed star, and everything it has ever consumed, is crushed into a region smaller than a single atom. Here, the gravitational pull becomes infinitely strong, and the curvature of space-time becomes infinite. In this realm, all the known laws of physics, including general relativity itself, break down completely. Concepts like space, time, and causality cease to have any meaning as we understand them. Scientists believe that to truly comprehend what happens at a singularity, we need a new theory of physics, one that successfully merges gravity with quantum mechanics, often called a theory of quantum gravity. Until that theory is found, the singularity remains a profound mystery, a wall beyond which our current science cannot see. It represents not just the heart of a black hole, but the very edge of our knowledge about the universe. Fact 4. The violent birth from a dying star. The most common type of black hole, the stellar mass black hole, is born from the death of a truly massive star. Throughout its life, a star exists in a delicate balance. The outward pressure from the nuclear fusion in its core pushes against the inward crush of its own gravity. For stars at least 20 to 25 times more massive than our Sun, This life ends in a spectacular fashion. When the star exhausts its nuclear fuel, the outward pressure ceases. With nothing left to support it, gravity wins this cosmic battle in an instant. The star's core collapses catastrophically upon itself in a fraction of a second. This collapse triggers a monumental explosion known as a Type II supernova, which blasts the star's outer layers into space, creating beautiful, expanding nebulae. This explosion is one of the most energetic events in the universe, briefly outshining its entire host galaxy. But while the outer layers are thrown outward, the core continues to collapse. Gravity is so overwhelming that it crushes the core beyond all known limits of matter, past the density of a neutron star, until it forms a singularity. The event horizon springs into existence around it, and a new black hole is born from the ashes of a brilliant, dead star, a silent monument to the power of gravity. Fact 5. Why our sun will not become a black hole. While the death of a massive star can create a black hole, our own sun is destined for a much calmer and quieter end. The reason lies entirely in its mass. Our sun is a medium-sized star, and it simply does not have enough gravity to crush itself into a singularity. It is not massive enough to trigger the kind of supernova explosion that precedes the birth of a stellar black hole. Instead, in about 5 billion years, after the sun has converted all the hydrogen in its core into helium, it will begin to swell. It will expand into a red giant, its outer layers growing so large they will likely engulf Mercury, Venus, and possibly even Earth. During this phase, it will fuse helium into heavier elements like carbon and oxygen. Eventually, the sun will exhaust this fuel as well. With no more fusion to power it, its outer layers will drift away into space, creating a beautiful, glowing shell of gas called a planetary nebula. Left behind in the center will be the star's hot, dense core, a white dwarf. This Earth-sized remnant will be incredibly dense, but it will be stable, supported by a quantum mechanical principle called electron degeneracy pressure. It will simply spend trillions of years slowly cooling down, eventually fading into a cold, dark ember known as a black dwarf, a peaceful end to its long life. Fact 6. The 3 tiers of cosmic titans. Black holes are not all the same size. They come in a fascinating range of classes, primarily defined by their mass. The smallest and most common are the stellar mass black holes. As we've learned, these are the remnants of massive stars and typically have a mass between 3 and 20 times that of our Sun. They are thought to be scattered throughout galaxies, silently wandering through the void. On the opposite end of the spectrum are the supermassive black holes. These are the undisputed titans of the cosmos, with masses ranging from millions to billions of times that of our Sun. Scientists are confident that a supermassive black hole resides at the center of nearly every large galaxy, including our own Milky Way. Their immense gravity acts as a galactic anchor, influencing the orbits of stars and the very formation of the galaxy around them. Between these two extremes lies a more mysterious and elusive class, intermediate mass black holes. With masses between 100 and a few 100,000 solar masses, they are the missing link. For a long time, their existence was only theoretical, but recent evidence has begun to confirm their presence, often found in the hearts of smaller, globular star clusters. Their discovery is crucial to understanding how the supermassive giants at the centers of galaxies could have grown so large, so quickly, in the early universe. Fact 7. The no-hair theorem simplicity. In the complex and bizarre world of astrophysics, black holes are governed by a principle of profound simplicity, famously summarized by the no-hair theorem. This theorem states that, regardless of the complexity of the matter that collapses to form it or falls into it, a stable black hole can be described by just 3 external properties: its mass, its electric charge, and its angular momentum, or spin. All other information, or hair, such as the chemical composition, shape, or texture of the matter that created it, is lost forever behind the event horizon. This means that 2 black holes with the same mass, charge, and spin are completely indistinguishable from each other, even if one was formed from a collapsed star and the other was formed from a giant cloud of cosmic dust or a collection of old planets. This elegant simplicity is both fascinating and frustrating for physicists. It makes black holes theoretically clean objects to study, but it also implies a profound loss of information from the universe, a puzzle known as the black hole information paradox. The idea that all the intricate details of matter can be erased, leaving only 3 simple numbers, makes black holes the ultimate minimalist objects in the cosmos. Fact 8. They are not cosmic vacuum cleaners. Fact 8. They are not cosmic vacuum cleaners. A common misconception, fueled by science fiction, is that black holes are like cosmic vacuum cleaners, aggressively roaming the universe and sucking up everything in their path. The truth is much less predatory. A black hole's gravity is powerful, but it still follows the same rules of physics as any other massive object. If you were to magically replace our Sun with a black hole of the exact same mass, the Earth and the other planets would not be sucked in. They would continue to orbit this new, dark center of our solar system in precisely the same paths they do now. The only difference would be the complete absence of light and heat, which would, of course, be catastrophic for life, but the orbit itself would remain stable. A black hole only becomes a threat when you get very close to it, inside a region called its gravitational sphere of influence. You must cross its event horizon to be captured. Stars, planets, and gas clouds can orbit a black hole safely for billions of years, just as we orbit the Sun. They are not hungry monsters, but rather passive giants, whose immense gravity only dictates the local flow of space-time. Their influence is powerful, but it is also predictable and localized. Fact 9. Finding the invisible. How do you find an object that is perfectly black and emits no light? Astronomers face this challenge by looking for the effects a black hole has on its surrounding environment. They act like cosmic detectives, searching for gravitational clues. One of the most common methods is to observe the motion of stars. If astronomers see a star orbiting an apparently empty point in space at high speed, it's a strong indication that a massive, unseen companion, likely a black hole, is present. This is precisely how the supermassive black hole at our galaxy's center was confirmed. Another powerful method is to look for accretion disks. When gas and dust are pulled toward a black hole, they don't fall straight in. Instead, they form a rapidly spinning, superheated disk of material around the event horizon. The friction within this disk heats the gas to millions of degrees, causing it to glow brightly in X-rays. Telescopes like the Chandra X-ray Observatory can detect this high-energy radiation, revealing the black hole's location like a lighthouse in the dark. More recently, the detection of gravitational waves by observatories like LIGO has opened a new window, allowing us to hear the ripples in space-time created when two black holes merge, providing direct and spectacular proof of their existence. Fact 10. The naming of a giant. The concept of an object so massive that light could not escape has been around for centuries, first proposed by John Michell in 1783. However, the term black hole is much more recent and has a specific origin story. For much of the 20th century, following Einstein's theory of general relativity, scientists referred to these theoretical objects with descriptive but uninspired names like dark stars or frozen stars. During a conference in 1967, a physicist named John Archibald Wheeler, who was a key figure in the development of theoretical physics, used the term black hole to describe the phenomenon of gravitational collapse. An audience member reportedly suggested the name after Wheeler's lecture, and he immediately adopted it for its simplicity and descriptive power. The name was a stroke of genius. It was catchy, evocative, and perfectly captured the two most essential features of the object: its nature as a gravitational trap, a hole in space-time, and its inability to emit light, making it black. The name spread rapidly through both the scientific community and public culture, cementing itself in our language. It's a perfect example of how the right name can transform an abstract scientific concept into something tangible and awe-inspiring for everyone. Part 2. The warping of reality. Fact 11. Bending the fabric of space-time. At the core of our understanding of black holes is Albert Einstein's general theory of relativity, which revolutionized our view of gravity. Before Einstein, gravity was seen as a simple force pulling objects together, as described by Isaac Newton. But Einstein proposed something far more profound. Gravity is not a force, but a consequence of the curvature of space-time. He suggested that space and time are not separate and absolute, but are woven together into a single, four-dimensional fabric. Massive objects, like stars and planets, create dips or curves in this fabric. Smaller objects, like planets orbiting a star, are simply following the straightest possible path along this curved surface, much like a marble rolling around a bowling ball placed on a stretched rubber sheet. A black hole takes this concept to its absolute extreme. The immense density of a black hole creates such a deep and severe curvature in space-time that it essentially becomes a bottomless pit. It's a region where the fabric of reality itself is bent to its breaking point. This is why nothing can escape. It's not about overcoming a force, it's about the fact that within the event horizon, all possible paths along the space-time fabric lead only in one direction, down into the singularity. Fact 12. Gravitational lensing, nature's telescope. Because black holes warp space-time so intensely, they have a dramatic effect on the light that passes near them. According to general relativity, light, like everything else, must follow the curves in space-time. When light from a distant star or galaxy passes close to a black hole, its path is bent. This phenomenon is called gravitational lensing. The black hole acts like a giant, invisible magnifying glass or distorted lens in space. This can lead to some fascinating visual effects. Depending on the alignment of the distant light source, the black hole, and the observer on Earth, the light can be smeared into arcs, magnified, or even appear as multiple distinct images of the same object. In a perfect alignment, the light can be distorted into a beautiful, complete circle of light known as an Einstein ring. For astronomers, gravitational lensing is a powerful tool. It not only provides strong evidence for the existence of black holes and confirms Einstein's theory, but it also allows us to see objects that would otherwise be too far away or too faint to detect. The black hole's immense gravity acts as a natural telescope, magnifying the distant universe for us. Fact 13. The slowing of time's river. One of the most mind-bending consequences of a black hole's extreme gravity is its effect on the passage of time. According to Einstein, time is not constant throughout the universe. It is relative and can be affected by both velocity and gravity. This effect is known as time dilation. The stronger the gravitational field, the slower time flows. This effect is real and has been measured even in the weak gravitational field of Earth. Clocks on GPS satellites run slightly faster than clocks on the ground. Near a black hole, this effect becomes extreme. If you were in a spaceship safely orbiting a black hole, your clock would tick noticeably slower than a clock on Earth. If you were to get even closer to the event horizon, the effect would be magnified dramatically. For an observer watching you from a safe distance, you would appear to move in slow motion. If you spent a few hours hovering near the event horizon and then returned to Earth, you would find that decades, or even centuries, had passed for everyone else. This is not science fiction. It is a direct prediction of general relativity. Near a black hole, time itself is stretched and distorted, demonstrating that even this most fundamental aspect of our reality is not immune to gravity's power. Fact 14. The tale of two travelers. The journey into a black hole is a true paradox, where the experience depends entirely on your point of view. Let's imagine two travelers, Anna and Ben. Anna is going to cross the event horizon, while Ben watches from a safe distance in his spaceship. From Anna's perspective, her journey would be surprisingly uneventful, at least at first if the black hole is supermassive. She would feel no jolt or bump as she crossed the event horizon. Her clock would tick normally, and she would see the universe outside her ship, albeit distorted by gravitational lensing. Her fate would be sealed, and she would eventually be crushed at the singularity, but the moment of crossing the boundary itself would be unremarkable for her. Ben's perspective, however, would be completely different. As he watches Anna's ship approach the event horizon, he would see her movements slow down dramatically due to time dilation. Her ship's light would become stretched to longer, redder wavelengths, an effect called gravitational redshift. She would appear to slow down more and more, taking an infinite amount of time to actually reach the horizon. He would never see her cross. Instead, he would see her image freeze, dim, and fade away over an eternity, a final, ghostly imprint on the edge of the abyss. Both experiences are physically real, a stunning demonstration of how reality is relative in our universe. Fact 15. The agony of spaghettification. While crossing the event horizon of a supermassive black hole might be gentle, approaching a smaller, stellar mass black hole would be a far more violent affair. The reason is due to something called tidal forces, which lead to a gruesome process appropriately named spaghettification. Tidal forces arise because the strength of gravity decreases with distance. As an object, say a spaceship, approaches a stellar mass black hole feet first, the gravitational pull on the astronauts' feet would be significantly stronger than the pull on their head. This immense difference in gravitational force would stretch the astronaut's body, pulling it apart with unimaginable power. The stretching would happen in one direction, while the sides of the body would be compressed inward. The The body would be elongated and thinned out, like a strand of spaghetti, until it was eventually torn apart into a stream of individual atoms. This stream of atoms would then spiral into the black hole. For a larger, supermassive black hole, the tidal forces at the event horizon are much weaker because the horizon is much farther from the singularity. An astronaut could cross the event horizon without being spaghettified, though they would inevitably face this fate as they continued their journey toward the center. It is a stark reminder of the raw, physical power exerted by these cosmic objects. Fact 16. The accretion disk's fiery glow. Black holes themselves are invisible, but they often create some of the brightest and most spectacular phenomena in the entire universe. When a black hole is situated in a region with abundant gas, dust, or a nearby star, its gravity will pull this material toward it. However, the matter rarely falls straight in. Due to its own momentum, it spirals inward, forming a flattened, rapidly rotating structure called an accretion disk. This disk is a place of extreme violence and energy. As the gas and dust particles orbit the black hole at incredible speeds, they rub against each other, creating immense friction. This friction heats the material to millions, or even billions, of degrees. At these temperatures, the matter glows with incredible intensity, releasing vast amounts of energy across the entire electromagnetic spectrum, particularly in the form of powerful X-rays. These accretion disks can shine so brightly that they outshine all the stars in their host galaxy combined. Such an object is known as a quasar, and they are some of the most luminous objects known. It is a profound irony that the darkest objects in the universe are responsible for creating the most brilliant displays of light, serving as cosmic beacons that allow us to locate them across billions of light years. Fact 17. Relativistic jets, cosmic cannons. In many cases, the intense activity within a black hole's accretion disk leads to another awe-inspiring phenomenon, the launching of relativistic jets. As matter swirls toward the event horizon, powerful magnetic fields, generated by the spinning disk and the black hole itself, become tightly wound and twisted. These magnetic fields can act like cosmic accelerators, corralling some of the superheated particles from the inner edge of the accretion disk and flinging them outward, away from the black hole's poles. These particles are ejected in two narrow, focused beams at speeds approaching the speed of light, hence the name relativistic jets. These jets are colossal structures, capable of traveling for hundreds of thousands of light years, far beyond the boundaries of their own host galaxy. They act like powerful cosmic cannons, pumping huge amounts of energy into the surrounding space. They can heat up intergalactic gas, trigger or suppress the formation of new stars, and shape the evolution of the entire galaxy. While it seems counterintuitive for an object known for pulling things in to be responsible for one of the universe's most powerful ejection mechanisms, it highlights the complex and dynamic relationship a black hole has with its environment. Fact 18. Frame dragging, the space-time vortex. The influence of a black hole extends beyond just its gravitational pull. A spinning black hole literally drags the fabric of space-time around with it. This bizarre effect, predicted by Einstein's theory of general relativity, is known as frame dragging or the Lenz-Thirring effect. Imagine placing a heavy ball in a vat of honey and spinning it. The honey closest to the ball would be dragged around, creating a small whirlpool. In a similar way, a rotating black hole twists the space-time in its vicinity, forcing anything that enters this region to be pulled along with its rotation. This creates a region outside the event horizon called the ergosphere. Within the ergosphere, space-time is being dragged around so fast that it is impossible for any object to remain stationary relative to a distant observer. To stay still, you would have to travel faster than the speed of light against the current of space-time, which is impossible. You are forced to move with the spin. This effect is a profound demonstration that space is not just an empty stage for events to unfold upon, but a dynamic, physical entity that can be twisted, stretched, and dragged by the massive, spinning objects that inhabit it. Fact 19. The photon sphere, a ring of light. Orbiting a black hole is a region where gravity is so strong that even light itself can be forced into an orbit. This region, located just outside the event horizon, is known as the photon sphere. At this precise distance, photons, particles of light, can travel in unstable circular paths around the black hole. If you were somehow able to position yourself at the photon sphere and look straight ahead, you would be able to see the back of your own head. The light from the back of your head would travel all the way around the black hole and arrive back at your eyes from the front. The orbit is highly unstable. However, any slight perturbation would cause a photon to either fly off into space or spiral downward across the event horizon, lost forever. The photon sphere is a critical feature and is directly related to the silhouette we see in images of black holes. The dark central shadow is the event horizon, and the bright, glowing ring around it is the light that has been bent by the black hole's gravity, originating from the accretion disk and other background sources, and smeared around this last possible orbit for light. It is a beautiful and eerie ring, marking the final boundary where light can still cling to the edge of the abyss. Fact 20. The sound of a black hole. It is a common saying that in space, no one can hear you scream. This is because sound, as we know it, is a pressure wave that needs a medium, like air or water, to travel through. Since space is mostly a vacuum, there is no conventional sound. However, this doesn't mean black holes are entirely silent in a cosmic sense. In 2003, NASA's Chandra X-ray Observatory made a remarkable discovery while observing a supermassive black hole at the center of the Perseus galaxy cluster. This cluster is filled with vast clouds of hot gas. The black hole was found to be emitting ripples of pressure through this gas, which are, in essence, sound waves. The note they detected was astonishingly deep, a B-flat, but 57 octaves below middle C. This is far too low for any human to hear, with a frequency that is over 1,000,000 billion times lower than the limits of human hearing. The waves were detected as faint, concentric rings in the X-ray emissions from the hot gas, similar to ripples on a pond. So while you wouldn't hear a black hole in the traditional sense, their immense power can generate the most profound and deepest bass note ever detected in the universe, a sound that resonates through entire galaxies. Fact 21. Stellar mass black holes, the silent wanderers. The most common members of the black hole family are the stellar mass black holes. These are the ghosts of once mighty stars, born from the supernova explosions of celestial giants. Typically weighing between 3 and 20 times the mass of our Sun, they are remarkably compact, with event horizons spanning only a few dozen kilometers. Because they are the result of a single star's death, they are scattered far and wide throughout galaxies. Scientists estimate there could be as many as 100 million of these silent wanderers drifting through our Milky Way alone. Most of them are isolated and therefore completely invisible, making them incredibly difficult to detect. We only become aware of them when they interact with their surroundings. If a stellar black hole happens to pass close to another star, it can begin to siphon material from its companion, creating a glowing accretion disk that shines brightly in X-rays. This creates a binary system known as an X-ray binary. By studying these systems, astronomers can measure the mass of the invisible object and confirm its identity as a black hole. Each one detected is another clue in the census of our galaxy's unseen population, a reminder of the violent, stellar past that created our galactic home. Fact 22. Supermassive black holes, the galactic anchors. At the heart of almost every large galaxy, including our own Milky Way, lies a gravitational monarch, a supermassive black hole. These are the titans of the black hole world, with masses that are simply staggering, ranging from millions to tens of billions of times the mass of our Sun. Their event horizons are vast, capable of encompassing the orbits of our solar system's planets. Unlike their stellar mass cousins, their origins are still a major puzzle in cosmology. They are too large to have been formed from a single star. Current theories suggest they may have started as smaller black holes in the early universe and grew to their immense sizes over billions of years, either by merging with other black holes or by continuously consuming vast quantities of gas, dust, and stars. Their gravitational influence is profound. They act as the central anchor for the entire galaxy, and the orbits of billions of stars are ultimately tied to their presence. The growth and activity of these central giants are also thought to be intimately linked to the evolution of the galaxy itself, regulating star formation and shaping the galactic landscape. They are not just objects within a galaxy, they are a fundamental part of its identity. Fact 23. Sagittarius A, our galaxy's gentle giant asterisk. Yes, our own Milky Way galaxy has a supermassive black hole at its center. It is named Sagittarius A asterisk, pronounced Sagittarius A star, and is located about 26,000 light-years from Earth in the direction of the Sagittarius constellation. For decades, astronomers observed stars at the galactic center moving at incredible speeds, orbiting a point that was seemingly empty. By tracking these orbits over many years, they were able to calculate the mass of the object they were circling, concluding it had to be a compact object with a mass of about 4 million times that of our Sun. The only known object that could be so massive yet so small was a supermassive black hole. Compared to the central black holes in some other galaxies, Sagittarius A* is relatively quiet and gentle. It is not currently feeding on large amounts of gas, so it does not have a bright, powerful accretion disk like a quasar. However, it is not completely dormant. Astronomers have observed occasional flares of X-ray light, indicating that it periodically snacks on small clumps of gas or unfortunate asteroids that wander too close. Its presence is a constant, quiet reminder of the immense power that resides at the very heart of our galactic home. Fact 24. The growth of giants. How does a black hole grow from a few million to many billions of solar masses? The growth of supermassive black holes is a story of cosmic consumption and violent mergers, playing out over eons. One primary method of growth is through the slow and steady accretion of gas and dust from the surrounding galaxy. In the dense, chaotic environment of a galactic center, vast clouds of gas can lose momentum and spiral inward, feeding the central black hole and causing it to gradually increase in mass over billions of years. When its accretion disk is brightly lit, we see it as a quasar. Another, more dramatic method of growth is through mergers. Galaxies are not static. They frequently collide and merge with one another. When this happens, the supermassive black holes at their respective centers will also begin a long, slow dance. They will orbit each other for millions of years, shedding energy in the form of powerful gravitational waves. Eventually, they will spiral inward and merge into a single, even larger black hole, an event that shakes the very fabric of space-time. This process is thought to be a key reason why the black holes in the largest galaxies have grown to be so colossally massive. Fact 25. The first ever image of a shadow. For all of human history, black holes were purely theoretical concepts, first in mathematics and later in astronomical inference. We knew they were there, but we had never truly seen one. That all changed on April 10, 2019. On that day, the Event Horizon Telescope, EHT, collaboration released the first ever direct image of a black hole and its shadow. The EHT is not a single telescope, but a planet-spanning network of radio telescopes, all working together to create a virtual telescope the size of Earth. This incredible resolving power was needed to capture an image of an object so far away. The target was the supermassive black hole at the center of a distant galaxy called Messier 87, or M87. This giant is 55 million light-years away and has a mass of 6.5 billion times that of our Sun. The image they revealed was breathtaking and iconic, a dark central region, the shadow of the event horizon, surrounded by a lopsided, glowing ring of superheated plasma. It was a stunning confirmation of Einstein's theories, a momentous technical achievement, and the first time humanity had ever laid eyes upon the edge of one of these cosmic abyss. It transformed the black hole from a theoretical abstraction into a real, tangible object in our universe. Fact 26. Hawking radiation, the faintest glow. For a long time, it was thought that black holes were the ultimate prisons, that nothing, once captured, could ever escape. This idea was challenged in 1974 by the brilliant physicist Stephen Hawking, who combined the theories of general relativity and quantum mechanics to make a startling prediction. He proposed that black holes are not completely black after all. Instead, they should faintly glow, emitting a trickle of thermal radiation, which was later named Hawking radiation. The theory is rooted in the bizarre nature of the quantum world, where pairs of virtual particles, one particle of matter and one of antiparticles, are constantly popping into and out of existence in empty space. Hawking realized that if a pair of these particles appeared right at the edge of the event horizon, one could be captured by the black hole while the other escaped into space. To an outside observer, it would look as if the black hole itself had just emitted a particle. By losing this tiny particle, the black hole loses an infinitesimal amount of energy, and therefore, mass. This groundbreaking idea meant that black holes were not eternal prisons and had a finite lifespan, a concept that fundamentally changed our understanding of these cosmic objects. Fact 27. The evaporation of an abyss. The discovery of Hawking radiation leads to a mind-boggling conclusion. Black holes can evaporate. However, this process is unimaginably slow, especially for the large black holes we observe in the universe today. The rate of evaporation is inversely proportional to the black hole's mass, meaning the smaller the black hole, the faster it radiates away its energy. For a stellar mass black hole, the amount of radiation it emits is incredibly feeble, far less than the cosmic microwave background radiation it absorbs. This means it is currently gaining mass, not losing it. But in the far, far future of the universe, when the background radiation has cooled and there is no more matter to feed on, the process of evaporation will become dominant. The timescale for a black hole the mass of our Sun to completely evaporate is a staggering 10 to the power of 67 years, a number so vast it is virtually impossible to comprehend. For the supermassive giants at the centers of galaxies, this process would take even longer, perhaps 10 to the power of 100 years, a period known as a Gugor years. In the cold, dark, final age of the universe, these evaporating black holes may be the very last sources of light and energy. Fact 28. The information paradox, a cosmic puzzle. Hawking radiation introduced a profound puzzle that has troubled physicists for decades: the black hole information paradox. One of the fundamental laws of quantum mechanics is that information can never be truly destroyed. You can burn a book, but in principle, all the information about its pages, the atoms, their energy, their spin, is still encoded in the resulting smoke, ash, and light, even if it's scrambled. But what happens when that book falls into a black hole? According to the no-hair theorem, all of its complex information is lost, and only its mass, spin, and charge are added to the black hole. Then, if the black hole eventually evaporates via Hawking radiation, that radiation is predicted to be purely thermal and random, containing no information about what fell in. This would mean the information from the book is gone from the universe forever, a violation of quantum law. This paradox creates a deep conflict between general relativity and quantum mechanics. Physicists have proposed many potential solutions. Perhaps the information is somehow preserved in the radiation, or stored in a remnant, or escapes through a link to another universe. But to this day, there is no consensus. It remains one of the deepest unsolved problems in theoretical physics. Fact 29. White holes, the cosmic fountain. In the mathematical realm of general relativity, every solution has its opposite. The opposite of a black hole, an object from which nothing can escape, is a white hole, a theoretical object from which things can only escape, but nothing can ever enter. A white hole would be a region of space-time that acts as a source, spewing out matter and light. You could never cross its event horizon from the outside, as you would be trying to enter a place from which everything is rushing outward at the speed of light. The concept of a white hole emerges naturally from the mathematics that describes an eternal, non-collapsing black hole, but their physical existence is highly debated. No astronomical process is known that could form a white hole, and they appear to be very unstable. Some speculative theories suggest that white holes could be the exit for matter that falls into a black hole, connecting them through a wormhole. Another idea is that the Big Bang itself might have been a kind of white hole event. While they remain firmly in the realm of science fiction and theoretical speculation, they serve as a fascinating reminder of the strange possibilities allowed by the laws of our universe. Fact 30. Wormholes, shortcuts through space-time. The idea of a wormhole, a tunnel connecting two distant points in space-time, is one of the most exciting concepts in theoretical physics. Officially known as an Einstein-Rosen bridge, this idea arises from the mathematics of black holes. In theory, a wormhole could connect two separate regions of our universe, or even connect our universe to another one entirely. The entrance to such a tunnel could be a black hole, while the exit could be a white hole. In this scenario, anything falling into the black hole would not be crushed at the singularity, but would instead travel through the throat of the wormhole and emerge from the white hole somewhere else. However, before you pack your bags for a trip across the galaxy, it's important to know that these types of wormholes are predicted to be incredibly unstable. They would collapse in on themselves the instant they formed, trapping any would-be traveler. To keep a wormhole open, you would need a type of exotic matter with negative energy density, a substance that has never been observed and may not exist. While wormholes are a staple of science fiction, their existence in our actual universe remains a highly speculative and unproven possibility. Fact 31. Micro-black holes, a fleeting possibility. Could black holes exist on a subatomic scale? According to some theories, it might be possible. Micro or quantum black holes are hypothetical, tiny black holes, far smaller than their stellar cousins, for which quantum mechanical effects play a major role. Some theories suggest that these tiny black holes could have been forged in the ultra-high energy environment of the early universe, moments after the Big Bang. If so, they could still exist today, potentially making up a component of the mysterious dark matter. Another thrilling possibility is that they could be created in powerful particle accelerators, like the Large Hadron Collider, LHC. By smashing particles together at nearly the speed of light, these machines recreate the energetic conditions of the early universe. If certain theories involving extra dimensions of space are correct, it might be possible to briefly create a microscopic black hole. However, there is no need to worry. Even if they could be created, they would be utterly harmless. Due to Hawking radiation, these tiny black holes would evaporate and disappear in a tiny fraction of a second, in a small, detectable puff of energy, before they could ever cause any damage. Fact 32. The ergosphere, stealing energy from a black hole. While nothing can escape from inside the event horizon, a spinning black hole offers a tantalizing possibility just outside of it, a region where energy can actually be extracted. This area is called the ergosphere, and it exists due to the frame-dragging effect, where the black hole's rotation drags space-time around with it. The ergosphere is an oblate spheroid shape that touches the event horizon at the poles and extends outwards at the equator. Within this region, space-time is dragged so fast that it's impossible to stand still. In 1969, physicist Roger Penrose proposed a clever way to exploit this, now known as the Penrose process. He theorized that if you were to send a probe into the ergosphere and have it drop a piece of matter into the black hole, the probe could emerge with more energy than it had when it went in. In essence, it would be stealing a tiny amount of the black hole's rotational energy. While the engineering required to do this is far beyond our current capabilities, it is theoretically sound. It shows that, under the right circumstances, even these ultimate sinks of matter can be forced to give up some of their immense energy. Fact 33. A link to dark matter? One of the greatest mysteries in modern cosmology is dark matter. It is an invisible substance that makes up about 85% of all matter in the universe. We know it exists because of its gravitational effects on stars and galaxies, but we don't know what it's made of. One intriguing, though not mainstream, hypothesis suggests that at least some of the dark matter could be made of primordial black holes. These are not the black holes formed from collapsing stars, but hypothetical black holes that may have formed in the first second of the universe's existence. In that chaotic, early period, tiny fluctuations in the density of matter could have been so extreme that some regions collapsed directly into black holes of various sizes, from the mass of an asteroid to thousands of times the mass of the Sun. If a large number of these primordial black holes were created, they would now be drifting through space, invisible and accounting for the missing mass we attribute to dark matter. While current observations from gravitational lensing surveys have placed tight constraints on this theory, it remains an exciting possibility, linking two of the most profound mysteries in the cosmos, the nature of black holes and the identity of dark matter. Fact 34. The discovery of gravitational waves. For most of history, our only way of studying the universe was by observing light, or electromagnetic radiation. But in 2015, humanity gained a completely new sense with which to perceive the cosmos. On September 14th of that year, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first ever gravitational waves. These were ripples in the fabric of space-time itself, predicted by Albert Einstein a century earlier. The signal, a faint tremor that stretched and compressed the observatory's 4-kilometer-long arms by less than the width of a proton, was traced back to one of the most violent events imaginable, the merger of two stellar mass black holes. This cataclysmic event, which had occurred over 1 billion years ago, sent a powerful shockwave of gravitational energy racing across the universe. The detection was a monumental achievement in science. Not only was it the first direct proof of the existence of gravitational waves, but it was also the first time we had ever observed a binary black hole system, and the first time we had witnessed the final moment of two black holes merging. It opened a brand new field of astronomy, allowing us to listen to the silent, gravitational symphony of the universe. Fact 35. The chirp of a cosmic collision. When two black holes spiral towards each other in the final moments before they merge, the gravitational waves they emit have a very specific and telling signature. As they get closer and orbit each other faster and faster, the frequency and amplitude of the space-time ripples increase. If we were to convert this gravitational wave signal into a sound wave, it would produce a sound known as a chirp. It's a low-frequency hum that rapidly rises in pitch and volume, culminating in a final, loud burst as the two black holes finally combine into one. This characteristic chirp signal is exactly what the LIGO detectors are designed to find. By analyzing the precise shape of this chirp, scientists can deduce an incredible amount of information about the event. They can calculate the masses of the two original black holes, how fast they were spinning, how far away the event occurred, and the mass of the final, merged black hole. Interestingly, the mass of the final black hole is always slightly less than the sum of the two initial masses. The missing mass, often equivalent to several times the mass of our Sun, is converted directly into pure gravitational energy, according to E equals mc squared, and radiated away in that final, powerful chirp. Fact 36. When a black hole dines on a neutron star. What happens when a black hole meets a neutron star, the second densest object in the universe? This cosmic mismatch results in a cataclysmic event that can be seen and heard across the universe. As the neutron star gets drawn closer, the black hole's immense tidal forces begin to tear it apart. The neutron star is shredded into a crescent of superdense, neutron-rich material, some of which is flung out into space while the rest is swallowed by the black hole. The ejected material, now free from the star's immense gravity, rapidly expands and cools. In this process, a series of nuclear reactions known as the R process takes place, forging many of the heaviest elements in the universe. Scientists believe that these specific events, the mergers of black holes with neutron stars, or two neutron stars merging, are the primary cosmic factories for elements like gold, platinum, and uranium. The event creates a brief but brilliant flash of light known as a kilonova, accompanied by a powerful burst of gravitational waves. Observing these events gives us a direct look at the origin of the precious metals we find on Earth, linking the densest objects in the cosmos to the jewelry we wear. Fact 37. A star torn asunder. While a direct collision with a black hole is rare, a star's close flyby of a supermassive black hole can be just as dramatic. If a star's orbit takes it too close to the galactic center, it can cross a boundary known as the tidal disruption radius. Within this region, the tidal forces of the supermassive black hole, the difference in gravitational pull on the near and far side of the star, become stronger than the star's own gravity that holds it together. The star is violently torn apart. This process is known as a tidal disruption event, or TDE. As the star is shredded, it is pulled into long, spaghetti-like streams of stellar gas. About the formation of this disk releases an enormous, multi-wavelength flare of radiation that can be detected by our telescopes. This flare can last for months or even years, slowly fading as the stellar material is consumed. These events provide astronomers with a unique opportunity to study otherwise dormant supermassive black holes and the extreme physics that occur in their immediate vicinity. Fact 38. Galactic feedback and star formation. Supermassive black holes are not just passive residents of their galaxies. They are active participants that can profoundly influence the galaxy's evolution. This interplay is known as galactic feedback. When a central black hole is actively feeding on gas and dust, its accretion disk and the powerful relativistic jets it launches pump enormous amounts of energy into the surrounding galaxy. These jets can flow into the vast clouds of cold gas that are the raw fuel for forming new stars. This process can have two opposing effects. In some cases, the pressure from the jets can compress the gas clouds, triggering a burst of rapid star formation. In other, more common cases, the energy from the jets and the radiation from the accretion disk can heat the gas up so much that it becomes too hot to collapse and form stars. This effectively shuts down or quenches star formation in the galaxy's central regions. This feedback loop creates a form of self-regulation, where the black hole's growth is tied to the galaxy's ability to form stars, and vice versa. It helps explain why the largest galaxies aren't still forming stars at a furious rate, suggesting a deep, symbiotic relationship between a galaxy and the giant at its heart. Fact 39. The most distant quasars. When we look at very distant objects in the universe, we are also looking back in time, because of the finite speed of light. Astronomers have used this principle to hunt for the most distant quasars, which are powered by actively feeding supermassive black holes, to understand the conditions of the early universe. To date, the most distant quasar ever discovered, named J0313-1806, is seen as it was just 670 million years after the Big Bang, when the universe was only about 5% of its current age. This ancient object is incredibly luminous and is powered by a supermassive black hole that had already grown to a staggering 1.6 billion times the mass of our Sun. The existence of such a massive black hole so early in cosmic history presents a major challenge to our theories of black hole formation and growth. It is incredibly difficult to explain how a black hole could have accumulated so much mass so quickly. Discoveries like this suggest that the seeds of supermassive black holes in the early universe may have been much larger than previously thought, or that they were able to feed on gas at a rate far exceeding our current models. These ancient titans are crucial clues in the ongoing quest to understand our cosmic origins. Fact 40. Rogue black holes, the intergalactic wanderers. Galaxies are not always peaceful places. They collide, merge, and interact in a complex cosmic dance. During these violent interactions, it is possible for a black hole to be ejected from its home galaxy and sent hurtling into the vast, dark expanse of intergalactic space. These lonely objects are known as rogue black holes. A common scenario for this to happen is during a galaxy merger. As the two central supermassive black holes spiral towards each other, the complex gravitational dynamics can sometimes give a gravitational kick to the newly merged, larger black hole, flinging it out of the new galaxy entirely. A similar process can happen on a smaller scale in dense star clusters, ejecting stellar mass black holes. These rogue black holes would be almost impossible to detect, as they would be wandering alone in the dark with very little matter to interact with. However, astronomers search for them by looking for gravitational lensing events, where a rogue black hole might briefly magnify the light of a distant star as it passes in front of it. While none have been definitively confirmed, their existence is a strong theoretical prediction, a testament to the chaotic and dynamic nature of the cosmos. Fact 41. Cygnus X1, the first and famous. While black holes were predicted by theory for decades, confirming their existence required finding a real one in the sky. The first strong candidate to be widely accepted as a black hole was an object named Cygnus X1. Discovered in 1964 as one of the brightest X-ray sources in the sky, its true nature was a mystery. Astronomers later identified its companion, a large, blue supergiant star. They observed that this star was wobbling, as if it were orbiting an unseen, compact object. By analyzing the orbit, they calculated that this invisible companion had to have a mass of about 15 times that of our Sun, yet it was far too small to be a normal star. The only known object that could fit these criteria was a black hole. The case became even stronger as they observed X-rays flickering rapidly, indicating that the source had to be incredibly small. The discovery led to a famous scientific bet in 1974 between Stephen Hawking, who bet against it being a black hole, and fellow physicist Kip Thorne, who bet it was. In 1990, as the evidence became overwhelming, Hawking conceded the bet. Cygnus X1 was our first confirmed glimpse of a black hole in action, a trailblazing discovery that paved the way for all that we have learned since. Fact 42. M87, the face of a giant asterisk. The supermassive black hole that holds the honor of being the first one ever directly imaged is located at the center of the galaxy Messier 87, or M87. This is not just any galaxy. M87 is a colossal elliptical galaxy, far larger and more massive than our own Milky Way, sitting about 55 million light-years from Earth. The black hole at its heart, known as M87*, is a true monster, weighing in at an astonishing 6.5 billion times the mass of our Sun. Its event horizon is so vast that it could easily swallow our entire solar system. But M87* is famous for more than just its size. It is also one of the most active black holes in our local universe. It is renowned for launching a spectacular relativistic jet of superheated plasma that travels for 5,000 light-years at nearly the speed of light. This jet, visible even in amateur telescopes, is a clear sign of the immense energy being unleashed by the material falling into the black hole. When the Event Horizon Telescope team chose their target, M87* was a perfect candidate. Its enormous size and activity meant its shadow would be just large enough to resolve with a planet-sized telescope, providing humanity with its first ever glimpse into the abyss. Fact 43. Turn 618, the ultramassive Titan. While M87* is enormous, the universe contains black holes that dwarf even it. One of the most massive black holes ever discovered is known as TN 618. This behemoth is classified not just as supermassive, but as ultramassive, a category reserved for black holes exceeding 10 billion solar masses. TUN 618 has an estimated mass of a staggering 66 billion times that of our Sun. It is located about 10.4 billion light-years away, meaning we see it as it was in the relatively early universe. Its event horizon has a radius of about 1,300 times the distance from the Sun to the Earth, large enough to contain thousands of solar systems. TUN 618 is the engine behind one of the most luminous quasars ever observed. The accretion disk of gas swirling into it is so bright that it shines with the light of 140 trillion suns, making it visible despite its immense distance. Objects like TUN 618 challenge our understanding of galaxy evolution. How could a black hole grow to be so monstrously large so early in the universe's history? It suggests that the conditions in the early cosmos may have been uniquely suited for rapid and efficient black hole growth, a puzzle that astronomers are still working to solve. Fact 44. The Great Annihilator near our galaxy's heart. Lurking near the center of the Milky Way is a black hole candidate with a truly fearsome nickname, the Great Annihilator. This object, officially designated 1E 1740.7 to 2942, is a stellar mass black hole located about 20,000 light-years from Earth. It earned its dramatic name due to a peculiar feature observed in its vicinity. The black hole is a powerful source of gamma rays, which are produced when particles of matter collide with their antimatter counterparts and annihilate each other. In this case, it is believed that the black hole is spewing out vast clouds of positrons, the antimatter equivalent of electrons. When these positrons encounter regular electrons in the surrounding space, they annihilate, creating a signature gamma-ray glow. This makes the Great Annihilator one of the brightest sources of antimatter observed in our galaxy. Like many stellar mass black holes, it is part of a binary system, siphoning material from a companion star to fuel its activity. Its dramatic name and its role as a cosmic antimatter factory make it a fascinating object of study for understanding the extreme physics at play near these compact giants. Fact 45. The hunt in globular clusters. Globular clusters are ancient, densely packed cities of stars that orbit the outskirts of galaxies. For a long time, astronomers believed that these crowded environments would be perfect breeding grounds for a special kind of black hole, the intermediate mass black hole. The theory was that in such a dense cluster, stars would frequently interact and collide, allowing a stellar mass black hole to grow steadily by merging with other black holes and consuming stars, eventually reaching a mass between 100 and 100,000 times that of the Sun. Finding these intermediate black holes is crucial, as they could be the seeds that eventually grow into the supermassive giants at the centers of galaxies. However, the hunt has proven to be incredibly difficult. While many candidates have been proposed, definitive proof has been elusive. The gravitational influence of such an object is hard to distinguish from the collective gravity of the many stars packed into the cluster's core. In recent years, however, more compelling evidence has emerged, including observations from the Hubble Space Telescope and detections of gravitational waves from the merger of mid-sized black holes, suggesting that these missing link objects do indeed inhabit the ancient hearts of globular clusters. Fact 46. Solving the information paradox. The black hole information paradox, which questions whether information is truly lost inside a black hole, has been a central problem in theoretical physics for nearly 50 years. While a definitive solution is still out of reach, recent developments have offered promising new avenues of thought. The original paradox arose because Hawking radiation seemed to be random, carrying no information. However, some physicists now believe the information is not lost, but is intricately encoded in the outgoing radiation in very subtle ways. One idea is that the black hole's event horizon is not as bald as the no-hair theorem suggests. It might be covered in a form of soft quantum hair, faint quantum excitations that retain a record of everything that has fallen in. As the black hole radiates, this information is gradually imprinted onto the outgoing Hawking particles. Another powerful concept is the holographic principle, which suggests that all the information contained within a volume of space, like a black hole, can be described by the physics on its boundary surface. This would mean the information isn't inside the black hole at all, but is stored on the event horizon itself, like data on a two-dimensional computer chip, ensuring it is never truly lost to the universe. Fact 47. Black holes in our imagination. Beyond their scientific importance, black holes have captured the human imagination like few other cosmic objects. They have become a cornerstone of science fiction, often used as plot devices representing the ultimate unknown, a gateway to another dimension, or a terrifying cosmic threat. The 1979 film The Black Hole portrayed a classic monster-like version, while Stanley Kubrick's 2001, A Space Odyssey used a mysterious monolith that hinted at a gateway, inspiring thoughts of transcendental journeys. More recently, the 2014 film Interstellar made a serious effort to depict a black hole with scientific accuracy. Working with physicist Kip Thorne, the filmmakers created a stunning and realistic visualization of a supermassive black hole named Gargantua, complete with a glowing accretion disk and the effects of gravitational lensing. The film also masterfully explored the concept of time dilation, where 1 hour on a nearby planet equaled 7 years on Earth. These representations, whether fantastical or scientifically grounded, play a crucial role. They translate complex physics into compelling narratives, inspiring public curiosity and encouraging a new generation to ponder the profound and beautiful mysteries of our universe. Fact 48. The future of black hole research. Our journey to understand black holes is far from over. In fact, a new golden age of discovery may just be beginning. The future of this research promises even more incredible insights. The Event Horizon Telescope collaboration is working to add more telescopes to its global network, which will increase the resolution of its images, potentially allowing us to see the shadow of our own galaxy's black hole, Sagittarius A*, and even create movies of matter swirling around the event horizon. In the 2030s, the European Space Agency plans to launch LISA, the Laser Interferometer Space Antenna. This will be a space-based gravitational wave observatory with arms millions of kilometers long, capable of detecting the low-frequency gravitational waves from the mergers of supermassive black holes, something ground-based observatories cannot do. This will allow us to map the history of galaxy mergers across cosmic time. Combined with next-generation optical and X-ray telescopes like the James Webb Space Telescope, astronomers will be able to probe ever closer to the event horizon, testing the limits of Einstein's theories and searching for new physics in the most extreme environments the universe has to offer. Fact 49. The final act of the universe. Black holes are not just fascinating objects in the current universe, they are predicted to be the main characters in its final act. According to the leading cosmological model, the universe will continue to expand, cool, and darken. In the far, far future, long after the last star has burned out and the galaxies have dissolved, black holes will be among the last complex objects remaining. This is known as the black hole era. During this unimaginably long period, these silent giants will slowly continue to accrete any stray matter, growing in the dark. But they too are not eternal. Due to Hawking radiation, they will slowly evaporate, converting their mass back into a faint trickle of particles and energy. The stellar mass black holes will go first, followed by the supermassive ones, in a process that will take googles of years. After the last and largest black hole has finally radiated away, the universe will enter its final state, known as the dark era. It will be a cold, vast, and near-empty place, containing only a dilute soup of photons, neutrinos, and other fundamental particles. The final whisper of the cosmos will be the slow death of its last black holes. Fact 50. The debate over black hole hair. The no-hair theorem elegantly states that a black hole is defined only by its mass, spin, and charge. However, this elegant simplicity is the root of the information paradox and has been challenged by physicists for years. The term hair refers to any other distinguishable feature or piece of information that a black hole might possess. While the classical theory remains robust, new ideas from quantum mechanics and string theory suggest black holes might have some form of quantum hair after all. This wouldn't be physical hair, but rather subtle quantum imprints on the event horizon or the surrounding gravitational field. For example, some theories propose the existence of soft hair, which are low-energy quantum excitations at the event horizon that can store information about the matter that fell in. If black holes do possess this hair, it could provide a mechanism for information to escape during evaporation, thus solving the paradox. This is an area of intense theoretical debate. Proving the existence of this quantum hair would be a monumental step towards a unified theory of quantum gravity, revealing that these cosmic giants are not the simple objects we once thought, but are in fact the most complex and efficient information scramblers in the universe. Fact 51. The cosmic censorship hypothesis. General relativity allows for a truly unsettling possibility, a naked singularity. This would be a singularity, a point of infinite density where the laws of physics break down, that is not hidden behind the cloaking shield of an event horizon. If such an object existed, it would be visible to the rest of the universe. We could, in principle, receive signals from a region where physics as we know it has ceased to exist, leading to unpredictable and potentially paradoxical outcomes. The implications are so profound that physicist Roger Penrose proposed the cosmic censorship hypothesis. This is not a proven law, but a conjecture which states that nature forbids the existence of naked singularities. It suggests that every singularity formed from a realistic physical process, like the collapse of a star, must be clothed by an event horizon. In essence, nature performs a form of censorship, hiding these points of infinite chaos from our view to preserve the predictability of the universe. While physicists have tried to find scenarios in computer simulations where naked singularities could form, they are usually unstable or require highly specific, unrealistic conditions. The hypothesis remains a cornerstone of black hole theory, a belief that the universe is, at its core, comprehensible. Fact 52. The innermost stable orbit. Can you orbit a black hole? Absolutely. Just like a planet orbits a star, a spaceship could maintain a perfectly stable orbit around a black hole, provided it stays at a safe distance. However, unlike with a normal star, there is a definitive point of no return for a stable orbit. As you get closer to a black hole, the curvature of spacetime becomes more extreme. Eventually, you reach a critical boundary known as the innermost stable circular orbit, or ISCO. Inside this boundary, no stable circular orbit is possible. Any object crossing the ISCO is destined to make a final, rapid plunge across the event horizon. The location of the ISCO depends on the black hole's mass and, crucially, its spin. For a non-spinning black hole, the ISCO is located at 3 times the Schwarzschild radius, the radius of the event horizon. For a maximally spinning black hole, frame-dragging effects pull the ISCO much closer, allowing matter to orbit safely much nearer to the event horizon. The ISCO is a region of immense physical importance. It is the inner edge of the accretion disk, where matter takes its final leap, releasing a huge burst of energy and creating the bright X-ray emissions that allow us to see these invisible giants. Fact 53. Black holes versus neutron stars. Black holes and neutron stars are the 2 possible endpoints for the death of a massive star, representing the ultimate victory of gravity. But there is a crucial line that separates them. A neutron star is an object of incredible density, formed when a star not quite massive enough to become a black hole explodes in a supernova. Its core collapses until it is about the size of a city, with a mass up to about 2.1 times that of our Sun. It is held up against further collapse by a quantum mechanical force called neutron degeneracy pressure. A black hole is what happens when gravity becomes even stronger. The dividing line is known as the Tolman-Oppenheimer-Volkoff limit. If a collapsing stellar core is more massive than this limit, roughly 2.1 solar masses, nothing, not even neutron degeneracy pressure, can stop the collapse. Gravity wins completely, and the core is crushed into a singularity. So, the key difference is this: a neutron star has a physical surface and is made of matter, albeit the densest matter known. A black hole has no surface. It is a region of warped spacetime defined by an event horizon, with a singularity at its center where matter as we know it ceases to exist. Fact 54. What a black hole feels like. Imagining what it would feel like to approach a black hole is a fascinating exercise in physics. The first thing to note is that it would not feel cold. Space is a vacuum, so heat transfer is slow. You would feel the cold of space, but not the black hole itself. The dominant sensation would be the overwhelming force of gravity, but not in the way you might think. You wouldn't feel heavy in the traditional sense. In free fall, you are weightless. The defining feeling would be the tidal force, the gravitational gradient across your body. As you approached, you would feel a gentle stretching sensation. This sensation would grow exponentially stronger, becoming a powerful and relentless pull, elongating your body from head to toe while squeezing you from the sides. This is the beginning of spaghettification. The sky around you would become a kaleidoscope of distorted starlight due to gravitational lensing. If there was an accretion disk, you would be bathed in intense heat and deadly radiation. But in the pure, empty space near the event horizon, the primary physical sensation would be the universe itself trying to pull you apart, a silent, irresistible force guiding you toward the inevitable singularity at the center. Fact 55. The story told by a chirp. The chirp sound of two merging black holes, detected as gravitational waves, is more than just a simple noise. It is a rich and detailed cosmic story, all told in less than a second. By meticulously analyzing the waveform of that chirp, scientists can reconstruct the entire event with astonishing precision. The starting frequency, or pitch, of the chirp tells them the initial masses of the two black holes. Heavier black holes orbit more slowly, starting at a lower pitch. The rate at which the pitch rises, the speed of the whoop, reveals the mass ratio between the two objects. The final, highest pitch and the abrupt stop of the signal mark the moment of merger and reveal the mass and spin of the newly formed, larger black hole. Even more subtle details are hidden within the wave. The precise shape of the ripples can tell scientists about the orientation of the black hole's spins, whether they were spinning in alignment or tumbling chaotically. The overall amplitude, or volume, of the signal allows them to calculate the distance to the event, and its location in the sky can be triangulated by comparing the signal's arrival time at different detectors on Earth. It is a complete astrophysical narrative, a ghost story written in the language of space-time, whispered across 1 billion light-years. Fact 56. The Planet 9 Hypothesis. One of the intriguing puzzles in our own solar system is the strange, clustered orbits of several distant objects in the Kuiper belt. These orbits suggest they are being gravitationally shepherded by a large, unseen object far beyond Neptune, nicknamed Planet 9. While the leading theory is that this is a yet-to-be-discovered planet about 5 to 10 times the mass of Earth, a more exotic and fascinating possibility has been proposed. Planet 9 could be a primordial black hole. A black hole with a mass of 5 Earths would be incredibly tiny, with an event horizon only about the size of a grapefruit. This would make it completely invisible to traditional telescopes, as it would emit no light and block very little. It would only be detectable by its gravitational influence. This hypothesis is testable. If such an object is orbiting our Sun, it should be surrounded by a faint, but detectable, halo of dark matter particles that have been captured by its gravity. Furthermore, as it moves through space, it might occasionally cause a brief gravitational lensing event on a background star. While the existence of Planet 9 is still a theory, the possibility that we have a tiny, primordial black hole as a neighbor is a thrilling idea. Fact 57. The universe's fastest scramblers. In the world of physics, a scrambler is a system that takes information and mixes it up, or randomizes it, very quickly. It has been theorized that black holes are the fastest and most efficient information scramblers in the entire universe. This idea connects the mysteries of gravity to the fields of quantum chaos and quantum computing. When information, like the quantum state of a particle, falls into a black hole, it doesn't just sit there. The immense gravity and chaotic environment near the singularity are thought to mix this information up with all the other information already inside, spreading it evenly and randomly across the event horizon in the shortest possible time allowed by the laws of physics. This concept is important for the information paradox. If the information is scrambled across the event horizon rather than being lost at the singularity, it could then be slowly and subtly encoded into the outgoing Hawking radiation as the black hole evaporates. This would mean that the information is never truly lost, just incredibly well hidden and difficult to decode. This view recasts black holes not as destroyers of information, but as the ultimate data encryption systems in nature. Fact 58. The shifting moods of a black hole. Active black holes are not static, unchanging eters. They are dynamic and complex systems that can exhibit different behaviors, almost like shifting moods. Astronomers have observed that stellar mass black holes in binary systems can switch between several distinct states, primarily known as the hard state and the soft state. In the soft state, the black hole is dominated by a cool, bright accretion disk that extends close to the innermost stable circular orbit. The X-ray light it emits is mostly stable and thermal. In the hard state, however, the inner part of the accretion disk seems to evaporate, replaced by a much hotter, fainter, and more diffuse cloud of plasma called a corona. This state is characterized by more variable and high-energy X-ray emissions. Crucially, the hard state is often associated with the launching of powerful, steady relativistic jets. Black holes can transition between these states over periods of weeks or months. Understanding what drives these transitions, perhaps a change in the rate of matter flowing from the companion star, is a key area of research. as it helps us understand the fundamental connection between how a black hole feeds and how it launches its galaxy-shaping jets. Fact 59. The shadow is a trick of light. The famous image of the M87 black hole reveals a dark central region, which is often called the black hole's shadow. It's natural to assume this shadow is simply the event horizon itself. However, the shadow we see is actually a trick of gravity and light, an optical illusion created by the black hole's extreme warping of space-time. The dark region is indeed a consequence of the event horizon, as it's the area from which no light can escape. But the size of this shadow is significantly larger than the event horizon itself, typically about 2.5 times bigger. This is because of the intense gravitational lensing that occurs just outside the horizon. The black hole captures not only the light that is aimed directly at it, but also light that passes very close by, pulling it back and absorbing it. This region of gravitational capture for photons is what defines the edge of the shadow. The bright ring we see is made of photons that pass just outside this capture zone, some of which have orbited the black hole multiple times before escaping towards our telescopes. So, when we look at that image, we are seeing the silhouette of the abyss, magnified and outlined by the very light it almost consumed. Fact 60. Measuring a black hole's spin. Determining a black hole's spin is crucial, as it holds clues about its history of mergers and feeding, and it dictates the structure of the space-time around it. But how do you measure the spin of a featureless, black object? Scientists use ingenious, indirect methods. One of the most powerful techniques is called X-ray reflection spectroscopy. This involves observing the X-rays emitted from the hot corona above the accretion disk. Some of these X-rays shine down onto the disk itself and are reflected, or echoed, back towards our telescopes. As they travel from the disk, their light becomes distorted by the black hole's extreme gravity and velocity. By analyzing how the X-ray spectrum is smeared and stretched, astronomers can determine how close the accretion disk gets to the event horizon. Since a spinning black hole drags the innermost stable orbit closer in, measuring this distance allows them to calculate the black hole's spin rate with remarkable precision. Another method involves analyzing the shape of the black hole's shadow. A spinning black hole should theoretically create a slightly asymmetrical, D-shaped shadow due to frame dragging, a feature astronomers are hoping to resolve with future observations. Fact 61. The colors of a cosmic spin. The lopsided, brighter on one side appearance of the ring in the M87 black hole image is not an accident or a flaw. It is a direct and beautiful confirmation of the black hole's spin. This effect is a result of relativistic beaming and the Doppler effect, applied to the material in the accretion disk. The gas in the disk is orbiting the black hole at speeds close to the speed of light. The material on one side of the disk is moving towards us, while the material on the other side is moving away. Just as the pitch of a siren changes as it moves towards or away from you, the color and brightness of light also change. The light from the gas moving towards us is boosted in energy and brightness, appearing brighter and shifted towards the blue end of the spectrum, a blue shift. The light from the gas moving away is sapped of energy, appearing dimmer and shifted towards the red end of the spectrum, a red shift. The Event Horizon Telescope was able to capture this effect, which is why the bottom part of the ring in the famous image is significantly brighter than the top. It is a visual signature of the dizzying dance of matter at the edge of space-time. Fact 62. The ring down, a final vibration. When two black holes collide and merge, the event is not quite over once they touch. The new, larger black hole that is formed is initially misshapen and unstable, like a water droplet that has just been struck by another. To settle into its final, stable, spherical shape, it needs to radiate away all of its imperfections and excess energy. It does this by vibrating, sending out a final, decaying burst of gravitational waves in a process called ring down. This phase is analogous to the sound a bell makes after it is struck. It rings with a specific tone and pitch that slowly fades away. For a black hole, these tones are a set of specific frequencies of gravitational waves, determined only by the final black hole's mass and spin, and nothing else. This makes the ring down phase an incredibly clean and powerful test of Einstein's general theory of relativity. By detecting and analyzing the frequencies of the ring down, scientists can verify if the final object behaves exactly as the theory predicts. Every gravitational wave detection from a merger so far has beautifully matched these predictions, providing some of the strongest evidence yet that our understanding of gravity is correct, even in the most extreme conditions. Fact 63. the magnetic engine of cosmic jets. One of the longest-standing puzzles about black holes was understanding the exact mechanism that launches the colossal relativistic jets from their poles. We now believe the key ingredient is magnetism. As gas and dust spiral inward within an accretion disk, the magnetic fields that are threaded throughout this material are carried along with it. The rapid spinning of the disk and the twisting of spacetime by the spinning black hole itself cause these magnetic field lines to become tightly wound, like a rubber band being twisted. This process can create a powerful, organized, and tightly coiled magnetic funnel around the black hole's poles. This magnetic structure then acts as a particle accelerator. It latches onto superheated plasma from the inner edge of the accretion disk and, using its immense magnetic pressure, flings this material outward along the path of least resistance, the poles, at nearly the speed of light. This process, sometimes called the Blandford-Znajek mechanism, is an incredibly efficient way of converting the rotational energy of the black hole and the gravitational energy of the infalling matter into the kinetic energy of a jet. It is a magnetic powerhouse, the engine behind the universe's most powerful cannons. Fact 64. Powering a future civilization? Could humanity ever harness the immense energy of a black hole? While still deep in the realm of theoretical physics and science fiction, several methods have been proposed. We've already encountered the Penrose process, which involves throwing matter into the ergosphere of a spinning black hole to extract rotational energy. A more explosive idea is the black hole bomb. This involves surrounding a spinning black hole with a giant mirror. If you then shoot a beam of light into the ergosphere, some of it would be amplified as it extracts energy. The mirror would reflect this amplified light back, and it would be amplified again, creating an exponential energy feedback loop that would eventually become incredibly powerful, though difficult to control. An even more distant future civilization might seek out evaporating micro-black holes. A black hole with the mass of a large mountain would have a temperature high enough to radiate energy at a tremendous rate, producing vast amounts of power in its final second of life. While all of these concepts are far beyond our current technological grasp, they are fascinating thought experiments that demonstrate the sheer amount of energy locked away within these gravitational titans, waiting to be understood and perhaps, one day, utilized. Fact 65. The view from within. What would an astronaut actually see during the final moments of a plunge across the event horizon? The view would be unlike anything else in the universe. Looking forward, in the direction of the singularity, the view of the outside universe would become compressed into a shrinking, circular window of intensely blue-shifted light. The sky would look like you were looking out of a fisheye lens, with the entire future history of the external universe playing out in fast forward within that bright circle. Looking backward, away from the singularity, the view would be even more bizarre. You would not see darkness. Instead, you would see the rest of the universe you had just left, but spread out all around you. Light from behind you, and from all sides, would have its path bent so severely by the black hole's gravity that it would be warped around to meet your eyes. You would essentially be able to see the entire universe contained in every direction you looked. As you approached the singularity, this view would become increasingly distorted and blue-shifted, the light reaching an almost infinite energy. It would be a final, dazzling, and terrifying spectacle before the end. Fact 66. Echoes from the edge of space-time. Even though we cannot see inside a black hole, astronomers have developed a clever technique to map the geometry of space-time right at the edge of the event horizon. This method is called X-ray reverberation mapping, or simply light echoes. It works by observing the superheated corona of plasma that sits above the accretion disk. This corona often produces intense, random flares of X-ray light. Some of this light travels directly from the flare to our telescopes on Earth. However, some of the light shines down, illuminating the spinning accretion disk below, and then reflects off it before traveling to us. This reflected light acts as an echo. Because it has to travel a longer path, it arrives at our telescopes a few moments later than the direct light from the flare. By measuring the tiny time delay between the initial flare and its echo, scientists can calculate the distance between the corona and the disk. As they watch the echoes coming from different parts of the disk, they can build up a map of the innermost region of the black hole system, probing the effects of warped spacetime and measuring the black hole's spin with a precision that was previously unimaginable. Fact 67. Illuminating the cosmic dark ages. The very first black holes in the universe may have played a critical role in one of the most important transformations in cosmic history, the epoch of reionization. For a few 100 million years after the Big Bang, the universe was filled with a dense, neutral fog of hydrogen gas, making it opaque to ultraviolet light. This was the cosmic dark ages. Eventually, the first stars and galaxies began to form, and their intense radiation started to ionize this hydrogen fog, stripping electrons from the protons and making the universe transparent, as it is today. While the first stars contributed to this process, many scientists believe they were not enough on their own. The first quasars, powered by rapidly growing supermassive black holes, would have been fantastically luminous sources of high-energy radiation. The intense light blasting from the accretion disks of these primordial black holes could have been a major driver of reionization, carving out huge bubbles of transparent, ionized gas in the early universe. In this sense, the darkest objects in the cosmos may have been instrumental in ending the cosmic dark ages and allowing the first light to travel freely across space. Fact 68. The neutral nature of black holes. The no-hair theorem states that a black hole has three properties: mass, spin, and electric charge. While theoretically a black hole could hold a large positive or negative charge, in reality, astronomers believe that nearly all black holes are electrically neutral. The reason for this is the universe's own balancing act. Imagine a black hole that somehow accumulated a large positive charge. Its powerful electric field would then begin to exert a strong influence on the surrounding space, which is filled with a thin plasma of charged particles. The positively charged black hole would fiercely repel other positive charges, like protons, but it would powerfully attract negative charges until the black hole had effectively neutralized itself, reaching a stable state with a net charge of zero. Because this neutralization process is so efficient, it is highly unlikely that any long-lived, significantly charged black hole exists in the universe today, leaving mass and spin as the two primary properties that truly define them. Fact 69. The gravitational wave kick. When two black holes merge, the event is not always perfectly symmetrical. If the black holes have unequal masses or are spinning in different orientations, the gravitational waves they emit during their final, violent moments can be launched preferentially in one direction. Just as the exhaust from a rocket engine creates thrust, this lopsided emission of gravitational waves creates a powerful kick that propels the newly formed, larger black hole in the opposite direction. This kick can be incredibly powerful, capable of launching the black hole at speeds of hundreds or even thousands of kilometers per second. If the kick is strong enough, it can be greater than the escape velocity of the host galaxy, meaning the new black hole is ejected entirely, doomed to wander the lonely void of intergalactic space as a rogue black hole. These kicks have profound implications for galaxy evolution. They could explain why some smaller galaxies don't appear to have central black holes. They may have been kicked out during a past merger. Astronomers are actively searching for evidence of these high-velocity, recoiling black holes to confirm this remarkable prediction of general relativity. Fact 70. Primordial black holes as galactic seeds. One of the great puzzles surrounding supermassive black holes is how they grew so large, so quickly in the early universe. Growing a black hole from the remnant of a single star to a billion solar masses in just a few 100 million years is extremely difficult. This has led to an alternative theory about their origins. They didn't grow from stellar mass black holes, but were instead seeded by much larger direct collapse black holes. This theory suggests that in the early universe, certain massive, primordial clouds of gas could have become unstable and collapsed directly into a black hole without first forming a star or going supernova. This process could create seeds, with masses of tens of thousands of times that of our Sun. Starting with such a massive seed would give these black holes a significant head start, making it much easier for them to grow into the billion solar mass giants we see powering the most distant quasars. While the exact conditions required for this to happen are rare, it provides a plausible solution to the timing problem, linking the formation of the first galactic giants to the unique environment of the infant universe. Fact 71. The holographic universe. The study of black holes has led to one of the most profound and mind-bending ideas in all of physics, the holographic principle. This principle was born from attempts to solve the information paradox. It suggests that all of the information contained within a three-dimensional volume of space can be described by the physics occurring on its two-dimensional boundary surface. The classic example is a black hole. According to the holographic principle, everything that falls into a black hole, and all the information that describes it, is not lost in a 3D singularity, but is instead perfectly encoded on the 2D surface of its event horizon, much like a three-dimensional hologram is projected from a two-dimensional film. Some physicists have taken this idea a step further, suggesting that our entire universe could be a hologram. In this view, the three-dimensional reality we experience could be a projection of physical processes and information that exist on a distant, two-dimensional cosmic horizon. While this is still a highly speculative and theoretical concept, it is a powerful idea that emerged directly from trying to understand the fundamental nature of black holes. Fact 72. A foam of virtual black holes. On the everyday scale, space-time appears smooth and continuous. But in the realm of quantum mechanics, at the smallest possible distance scale, known as the Planck length, space-time itself is thought to become a chaotic and turbulent place. Physicist John Wheeler described this as quantum foam, a sea of roiling energy fluctuations where the geometry of space and time is constantly changing. Within this quantum foam, it's theorized that tiny, virtual black holes could be constantly popping into existence, living for an infinitesimal moment, and then disappearing again. These would not be the stable black holes formed from stars, but transient fluctuations of gravitational energy, governed by the uncertainty principle. They would have a lifespan of only about 10 to the power of -43 seconds. While we could never observe them directly, their fleeting existence, if real, would have a fundamental impact on the nature of space-time. They would represent the ultimate convergence of gravity and the quantum world, and their study is a key part of the quest for a theory of everything, suggesting that the fabric of reality is far stranger and more dynamic than it appears. Fact 73. What is the singularity, really? General relativity tells us that the center of a black hole is a singularity, a point of infinite density. However, most physicists believe this is not the complete picture. The concept of infinity in a physical theory is often a sign that the theory itself is breaking down and a deeper understanding is needed. To truly know what lies at the heart of a black hole, we need a theory of quantum gravity. Some speculative theories offer intriguing alternatives to the classical singularity. One idea is the Planck star, which suggests that as matter collapses, it doesn't reach infinite density. Instead, it reaches a fantastically dense but finite state, governed by quantum effects, with a size close to the Planck length. In this scenario, the collapsing matter would then bounce and begin to expand, turning the black hole into a white hole after a very long time. Other theories propose that the singularity could be a gateway to a new, baby universe, or that matter is transformed into an exotic state, like a fuzzball of fundamental strings as predicted by string theory. The true nature of the singularity remains perhaps the greatest unanswered question in the physics of black holes. Fact 74. The black hole bomb. One of the most mind-bending thought experiments in physics is the concept of a black hole bomb. This is a theoretical mechanism for extracting an immense amount of energy from a spinning black hole. The idea relies on a phenomenon called superradiant scattering. If you send a wave, such as a light wave or a gravitational wave, with the right properties into the ergosphere of a spinning black hole, it can bounce off and emerge with more energy than it had when it went in. It effectively steals a tiny amount of the black hole's rotational energy. To turn this into a bomb, you would theoretically need to build a giant, perfectly reflective mirror that completely surrounds the black hole. When you send a single light wave into this setup, it gets amplified by the ergosphere, hits the mirror, and is reflected back to be amplified again. This process repeats, creating an exponential and runaway amplification of energy. The trapped light would become incredibly powerful, until it either overwhelmed the mirror's ability to contain it or was released in a controlled manner. While building such a mirror is technologically impossible, the principle highlights the astonishing amount of energy locked away in a black hole spin, waiting to be tapped by a sufficiently advanced civilization. Fact 75. A creator and a destroyer. The relationship between a supermassive black hole and its host galaxy is a delicate dance of creation and destruction. Through a process called galactic feedback, the black hole can act as both a stellar nursery and a stellar executioner. The destructive mode, known as negative feedback, is more common. As the black hole feeds, The immense energy from its accretion disk and jets heats up the gas in the galactic center, preventing it from cooling and collapsing to form new stars. This can effectively quench star formation and stunt a galaxy's growth. However, black holes can also provide positive feedback. The very same jets that can heat gas can also, under the right conditions, trigger the birth of stars. As a jet plows through the interstellar medium, it can create a high-pressure shockwave that compresses the vast clouds of gas and dust it encounters. This compression can be the catalyst needed to kickstart gravitational collapse within these clouds, leading to a burst of new star formation in the jet's path. So, the same black hole can be seen suppressing star formation in its immediate vicinity while simultaneously igniting it farther out, playing a complex and crucial role in sculpting the stellar landscape of its entire galaxy. Fact 76. The powerful winds of an accretion disk. It is a common misconception that all matter caught in a black hole's accretion disk is doomed to fall past the event horizon. In reality, these disks are incredibly violent and inefficient feeding systems. A significant portion of the gas and dust that spirals inward is actually blown back out into the galaxy in the form of powerful, high-speed winds. These winds are driven by several forces. The intense radiation pouring out of the inner, superheated part of the disk can exert a powerful pressure on the outer, cooler gas, effectively pushing it away. Additionally, complex magnetic fields embedded within the disk can act like a slingshot, flinging material out from the disk surface. These accretion disk winds can travel at thousands of kilometers per second and carry a substantial amount of mass away from the black hole each year. Like the jets, these winds are another important form of galactic feedback. They enrich the host galaxy with heavy elements forged in the disk, clear out gas from the central regions, and regulate the amount of fuel available for the black hole to consume, helping to control its long-term growth. Fact 77. The ultimate breaking point. There is a fundamental speed limit in the universe, the speed of light. Similarly, there is a fundamental mass limit for a neutron star, a point beyond which it is crushed into a black hole. This breaking point is known as the Tolman-Oppenheimer-Volkoff (TOV) limit. It represents the absolute maximum mass that a non-rotating neutron star can sustain before its own gravity overwhelms the internal quantum pressure that supports it. This supporting force, known as neutron degeneracy pressure, is the result of a quantum rule that forbids neutrons from being packed too tightly together. For a long time, the exact value of the TOV limit was uncertain, as it depends on our poorly understood physics of ultradense matter. However, thanks to observations of gravitational waves from merging neutron stars and other astronomical data, scientists have constrained this limit to be approximately 2.16 times the mass of our Sun. Any stellar remnant with a mass below this limit can exist as a stable neutron star forever. But if a collapsing star's core is more massive, or if a neutron star accretes enough matter from a companion to push it over this line, its fate is sealed. Gravity wins the final battle, and the object will inevitably collapse into a black hole. Fact 78. The temperature of a shadow. Does a black hole have a temperature? In a classical sense, no. An object's temperature is related to the thermal motion of its particles, and a black hole is a region of space-time. But in the quantum world, the answer is a definitive yes. Through the Bekenstein-Hawking formula, we know that a black hole has a temperature that is directly related to the surface gravity at its event horizon. This temperature is a result of the quantum effect of Hawking radiation. However, this temperature has a very peculiar and counterintuitive property. It is inversely proportional to the black hole's mass. This means that the larger and more massive a black hole is, the colder it is. A stellar mass black hole with the mass of our Sun would have a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. This is far, far colder than the cosmic microwave background radiation that fills space, which is about 2.7 Kelvin. Therefore, all existing stellar and supermassive black holes are currently absorbing far more energy from the universe than they are emitting, causing them to get colder and more massive over time, not hotter. Fact 79. The stellar vampires. Most stellar mass black holes drift through the galaxy in complete isolation, making them nearly impossible to find. Our best laboratories for studying them are in systems where they are not alone. These are known as X-ray binaries, and they occur when a black hole is in a close orbit with a normal star. In this cosmic pairing, the black hole becomes a stellar vampire. Its powerful gravity latches onto the outer layers of its companion star, siphoning off a steady stream of gas. This stolen material does not fall directly into the black hole but forms a bright, hot accretion disk around it. As this disk radiates an immense amount of energy in the form of X-rays, it becomes a beacon that our telescopes can easily detect against the dark of space. By studying the light from the visible companion star, observing its orbit and how it's being pulled by its unseen partner, astronomers can precisely calculate the mass of the invisible object. If the mass is significantly above the 3 solar mass limit for a neutron star, they can confidently identify it as a black hole. These systems are a primary source of real-world data on stellar mass black holes. Fact 80. A rhythmic flicker in the dark. The light from a black hole's accretion disk is not always a steady, constant glow. When astronomers observe these systems with X-ray telescopes, they often detect a rapid, rhythmic flickering in the light's intensity. These are known as quasi-periodic oscillations, or QPOs. The brightness of the inner disk can oscillate on timescales of milliseconds, producing a signal that is almost, but not quite, perfectly periodic. While the exact cause of these QPOs is still a subject of intense research, they are believed to be connected to the fundamental physics of the material orbiting at the very edge of the event horizon. They could be the signature of hot spots or waves moving through the plasma in the innermost stable orbit, or they might be related to the wobble of spacetime itself as it's being dragged by the spinning black hole. Whatever their origin, QPOs are incredibly valuable. The frequency of these oscillations is directly tied to the properties of the black hole itself, such as its mass and spin. They are like a natural clock, ticking away in the most extreme gravitational field imaginable, providing a direct probe of Einstein's theory of general relativity. Fact 81. Black hole seismology. Just as seismologists study the waves from an earthquake to learn about the interior of the Earth, astrophysicists can use the gravitational waves from a black hole merger to probe the properties of the final, newly formed black hole. This emerging field is sometimes called black hole seismology. The key to this is the ring-down phase of the merger. The signal from the ring-down is not just a single tone. It is a complex sound made up of a fundamental frequency and several higher-pitched overtones, much like the sound of a ringing bell. According to general relativity, the exact frequencies and decay times of these different tones are rigidly determined by only 2 properties: the final black hole's mass and its spin. By detecting multiple tones in the ring-down signal, scientists can test this prediction with incredible precision. They can measure the mass and spin from one tone, and then check if the other tones have the exact frequencies predicted by the theory. This provides a powerful, independent test of the no-hair theorem and allows us to verify that the final object is indeed the simple black hole described by Einstein's equations, with no hidden surprises. Fact 82. Spin boosts the brightness. The spin of a black hole does more than just drag spacetime around with it. It has a profound impact on how brightly the black hole can shine. The key is the location of the innermost stable circular orbit, or ISCO. For a non-spinning black hole, the ISCO is relatively far out. This means that gas in the accretion disk takes its final plunge from a significant distance, releasing a certain amount of energy as light. However, for a rapidly spinning black hole, the frame-dragging effect allows matter to orbit safely much closer to the event horizon before it becomes unstable. Because the most intense energy release happens in these final, frantic moments of the inward spiral, a disk around a spinning black hole is able to convert the potential energy of the gas into radiation far more efficiently. A maximally spinning black hole can be more than 10 times more efficient at converting matter into energy than a non-spinning one. This means that for the same amount of fuel being consumed, a spinning black hole will power a significantly brighter and more powerful quasar. This increased efficiency also helps explain how supermassive black holes in the early universe were able to grow so large, so quickly. Fact 83. Breaking the cosmic speed limit. There is a theoretical speed limit on how fast a black hole can feed, known as the Eddington limit. This limit represents a state of equilibrium. As a black hole consumes gas, its accretion disk heats up and radiates light. This light itself exerts an outward pressure. The Eddington limit is the point at which the outward pressure of the radiation produced by the accretion exactly balances the inward pull of the black hole's gravity on the surrounding gas. If a black hole tries to feed faster than this limit, the radiation pressure should become so intense that it blows away any additional fuel, effectively choking off its own food supply. For a long time, This was considered the absolute maximum rate of growth. However, astronomers have discovered objects, particularly in the early universe, called ultraluminous quasars, that appear to be shining with a brightness that far exceeds their Eddington limit. This suggests that black holes have found ways to cheat the system. They might do this through super-Eddington accretion, where the infalling gas is not smooth and uniform, but clumpy, allowing some of it to sneak past the radiation pressure and feed the black hole at a much higher rate. Fact 84. A turbulent atmosphere. The ergosphere of a spinning black hole is one of the most exotic environments in the universe. It is more than just a region of swirling space-time. It can be thought of as a turbulent, energy-rich atmosphere. The rotational energy within this region is so immense that it can actually create matter. Similar to the way virtual particles pop into existence in empty space, the energy in the ergosphere can be converted into real particle-antiparticle pairs. In a process theorized by physicist Yakov Zeldovich, if a particle pair is created here, it's possible for one of the particles to be given a negative energy trajectory and fall into the black hole, while the other particle escapes with more energy than the original pair had. This is another way of saying that the escaping particle has stolen energy from the black hole's spin. This process would cause the black hole to spin down over time, converting its rotational energy into a constant stream of particles radiating from its atmosphere. This means a spinning black hole is not truly quiescent. Its ergosphere is a dynamic and chaotic region, a physical link between the black hole's immense rotational power and the rest of the universe. Fact 85. Black holes in higher dimensions. Our experience of the universe is in 3 dimensions of space and 1 of time. But some advanced theories in physics, like string theory, propose the existence of additional, hidden spatial dimensions that are curled up and too small for us to perceive. This raises a fascinating question. What would a black hole look like in a universe with more dimensions? The answer is that it would be a very different object. A higher dimensional black hole would have a different shape and different properties. For example, Stephen Hawking showed that a 5-dimensional, spinning black hole would not be a sphere, but would have the shape of a spinning ring. Furthermore, some theories suggest that these higher dimensional black holes would be much less stable than their 3D counterparts. They could potentially break apart into smaller black holes or radiate energy in unique ways. The search for these unique signatures is one of the goals of experiments at the Large Hadron Collider. If scientists were to create a microscopic black hole that evaporated in a pattern that didn't match the predictions for 3D space, it would be powerful evidence for the existence of these hidden extra dimensions. Fact 86. The ultimate computer. In the quest for ever more powerful computing, physicists have considered the ultimate physical limits of information processing. This line of inquiry has led to a startling conclusion. A black hole can be thought of as the most powerful and efficient computer possible in our universe. Firstly, it is the ultimate information storage device. A principle known as the Bekenstein bound states that there is a maximum amount of information that can be stored in a given region of space, and a black hole is the one object that perfectly meets this theoretical limit. All the information is packed as densely as the laws of physics will allow. Secondly, black holes are believed to be the universe's fastest scramblers, meaning they process or randomize information at the highest possible speed. This theoretical maximum speed is related to the black hole's temperature and size. This suggests that a black hole could function as a natural quantum computer of unimaginable power and efficiency. While we could never retrieve an answer from inside the event horizon, this idea creates a deep and unexpected link between gravity, thermodynamics, and information theory, suggesting that the same laws that govern these cosmic giants also govern the fundamental limits of computation. Fact 87. Are we living inside a black hole? This is one of the most speculative but intriguing questions in cosmology. Could our entire observable universe exist within the event horizon of a much larger black hole? This idea, known as the black hole cosmology or Schwarzschild cosmology, arises from the mathematical similarities between the Big Bang and black holes. Both involve a singularity, a point of infinite density from which everything expands. According to this model, the Big Bang was not the beginning of everything, but rather the formation of a singularity and an event horizon within a larger parent universe. We, living inside this event horizon, would perceive the expansion of space as the aftermath of our Big Bang and would be unable to see anything outside our cosmic horizon. This model is not widely accepted and has several theoretical challenges, such as explaining the observed flatness and uniformity of our universe. However, It is a fascinating thought experiment that challenges our conventional view of the cosmos. It suggests that what we consider to be the entirety of existence could simply be one isolated, self-contained object within a much grander, and potentially eternal, multiverse. Fact 88. The cosmic sensor. Why is our universe so predictable? Why do the laws of physics seem to work so consistently everywhere we look? Part of the reason might be the universe's own self-preservation mechanism, which physicist Roger Penrose termed the cosmic censorship hypothesis. As we've learned, this hypothesis proposes that every singularity, with its chaotic and physics-defying nature, must be hidden from our view behind an event horizon. A black hole acts as a cosmic sensor, placing a veil over the parts of the universe where predictability breaks down. If a naked singularity were to exist, it could theoretically influence our universe in completely random and acausal ways, making it impossible to predict the future from the past. The fact that our universe appears so orderly and that physical laws are so reliable is, in itself, circumstantial evidence for this principle. While it remains an unproven hypothesis, it is a deep and philosophical idea. It suggests that the existence of event horizons is not just a curious feature of gravity, but a fundamental necessity for a universe that can be understood by the beings living within it. Fact 89. Gravity is a path, not a pull. One of the most persistent misconceptions about black holes is that they suck things in. This word conjures the image of a cosmic vacuum cleaner, an active force pulling objects from afar. But this is not how gravity works. A black hole's gravity is immense, but it is also passive. It does not reach out and grab things. Instead, it creates a deep curvature in the fabric of space-time around it. Objects are not sucked in, they fall in. An object in space, like a planet or a spaceship, is always following the straightest possible path through space-time. Near a black hole, all paths that cross the event horizon lead inward. Think of it less like a vacuum and more like a river leading to a waterfall. If you are far from the waterfall, you can paddle on the river and easily escape its current. But there is a certain point, the edge of the falls, where the current becomes too strong, and no amount of paddling can save you. The event horizon is that edge. An object falls into a black hole simply because its path through the universe has led it to a region of space-time so warped that the only future direction available is in. Fact 90. The most perfect silence. We have spoken of the sound of a black hole, the gravitational wave chirps of a merger, or the deep note resonating through a gas cluster. But in a more direct, physical sense, a black hole is a place of the most profound and perfect silence imaginable. Sound requires a medium to travel, a vibration of particles to carry the wave. The vacuum of space is already silent, but a black hole's event horizon takes this to an entirely new level. It is the ultimate one-way membrane. While sound waves from an exploding star could travel through a gas cloud towards a black hole, the moment those vibrations cross the event horizon, they are captured forever. No sound, no information, no echo can ever return. If you were to hover at the edge, the universe behind you could be filled with cataclysmic, noisy events, but the region in front of you would be a wall of absolute acoustic nothingness. It is the most perfect soundproofed room in the cosmos, a place where all vibrations, all sounds, and all whispers of the universe come to a final, definitive end. Fact 91. A black hole made of light. Can you create a black hole from something other than matter? In theory, yes. Einstein's famous equation, E equals mc squared, tells us that energy and mass are two sides of the same coin. This means that a sufficiently high concentration of any form of energy can, in principle, create gravity and warp space-time. This leads to the theoretical concept of a Kugelblitz, a German word meaning ball lightning. A Kugelblitz is a hypothetical black hole formed not from the collapse of a star, but from an immense concentration of pure energy, specifically light. If you could focus an unimaginable amount of high-energy radiation, like gamma rays, into a point smaller than an atomic nucleus, the energy density would become so great that it would collapse under its own gravity and form an event horizon and a singularity. The amount of energy required is colossal, far beyond anything we can currently generate. However, the Kugelblitz remains a fascinating prediction of general relativity. It implies that the raw material for a black hole is not necessarily matter, but simply a sufficient density of energy in any form, reinforcing the deep and fundamental connection between energy, mass, and the geometry of space-time. Fact 92. Our closest known dark neighbor. For a long time, the closest known black hole was thought to be thousands of light years away. But recent, incredibly precise observations have revealed a much closer neighbor. The current record holder for the closest known black hole to Earth is an object named Gaia BH1. It is located approximately 1,560 light-years away in the constellation Ophiuchus. While this sounds far, in galactic terms, it is in our cosmic backyard. Gaia BH1 is a stellar mass black hole, about 10 times the mass of our Sun. It is completely dormant and invisible. It was discovered not by seeing it, but by watching its companion, a normal, sun-like star. Astronomers using the Gaia Space Telescope noticed that this star had a subtle but distinct wobble, as if it were being tugged by an unseen object in a wide orbit. Follow-up observations confirmed that the only object massive enough to cause this wobble, yet be completely invisible, was a black hole. The discovery of such a close and dormant black hole suggests there may be many more like it, silently orbiting among the stars, waiting to be found. Fact 93. The Black Hole Starship. Could a black hole one day be the engine that takes humanity to the stars? In the far future, this science fiction dream might be a theoretical possibility. The concept revolves around using a small, artificial black hole as a power source for an interstellar starship. If you could create a microscopic black hole, it would radiate energy via Hawking radiation at a tremendous rate. The smaller the black hole, the hotter and more powerful its radiation. By carefully feeding this tiny black hole matter, you could control its output. This intense radiation, composed of a shower of high-energy particles and gamma rays, could then be focused by a powerful magnetic field or a parabolic reflector to create an incredibly efficient and powerful form of thrust. The ship would essentially be riding on a controlled beam of particles created by its own miniature sun. The challenges, of course, are immense. We would first need a way to create and contain a microscopic black hole and then a way to feed it with perfect precision. While purely speculative, the idea of a black hole starship represents the ultimate application of our understanding of gravity, a way to turn the universe's most powerful force of destruction into a tool for exploration. Fact 94. The firewall paradox. Just when physicists thought the information paradox was the biggest puzzle, a more fiery and controversial idea emerged: the firewall paradox. This thought experiment takes a deeper look at the quantum mechanics of the event horizon. It argues that for information to truly be preserved and escape via Hawking radiation, the laws of quantum mechanics would require the event horizon to be a place of immense energy, a literal firewall of high-energy particles. This presents a stark contradiction to Einstein's theory of general relativity. One of Einstein's key principles, the equivalence principle, states that an astronaut freely falling across an event horizon should experience nothing unusual, as they are in a state of weightlessness. However, the firewall paradox suggests that this astronaut would not have a gentle passage, but would instead be instantly incinerated upon touching the horizon. This creates a deep and troubling conflict between three fundamental pillars of modern physics: the equivalence principle, the preservation of quantum information, and our current understanding of quantum field theory. Physicists are now grappling with this puzzle, which suggests that one of these core principles must be wrong, and that there is still something profound we are missing about the nature of space-time. Fact 95. The seeds of life? We often think of black holes as purely destructive forces, the endpoint of matter. But could they, in a grand cosmic sense, actually be a source of life? This highly speculative but beautiful idea connects the largest and smallest scales of the universe. The center of a galaxy, where the supermassive black hole resides, is a crucible of star formation and death. Over billions of years, this region becomes heavily enriched with metals, the astronomical term for elements heavier than hydrogen and helium, which are essential for forming planets and life. The powerful relativistic jets launched by the central black hole can then act as a galactic distribution system. These jets plow through the galaxy, carrying these life-giving heavy elements far from the chaotic center and depositing them into the calm, distant gas clouds of the galactic halo. This process could seed these primordial clouds with the raw materials: carbon, oxygen, iron, needed to form new generations of stars, rocky planets, and, eventually, biology. In this view, the black hole acts as the galaxy's heart, pumping the essential nutrients for life far and wide, ensuring that the seeds of creation are spread even by the most powerful forces of destruction. Fact 96. Gravitational atoms. In our familiar world, atoms are formed by electrons orbiting a central nucleus, bound by the electromagnetic force. But what if you could replace the nucleus with a microscopic black hole and the electromagnetic force with gravity? This is the theoretical concept of a gravitational atom. In this setup, a fundamental particle, like an electron or a neutrino, would orbit a tiny black hole, not because of electric charge, but because of their mutual gravitational attraction. For this to be stable and for quantum effects to be significant, the black hole would have to be incredibly small, perhaps with the mass of a large asteroid compressed to a subatomic size. The particle would occupy distinct energy levels or orbitals, just like in a regular atom, but these levels would be defined by the laws of gravity instead of electromagnetism. While these are purely theoretical objects, their study is important. They represent a unique intersection of quantum mechanics and gravity, allowing physicists to explore how these two great theories might behave together. The gravitational atom is a perfect thought experiment, a bridge between the world of the very small and the world of the very massive. Fact 97. Are black holes fuzzballs? String theory, one of our leading candidates for a theory of quantum gravity, offers a radical and elegant solution to the singularity and the information paradox. It proposes that black holes are not what they seem. In this view, when a star collapses, it does not form a point of infinite density. Instead, the matter is transformed into a tangled, vibrating ball of fundamental strings, the basic ingredients of all matter and energy in this theory. This object is called a fuzzball. A fuzzball would have no singularity and no true event horizon. It would be a solid, albeit fuzzy, object with a real physical surface, much like a superdense, exotic star. The size of this fuzzball would be the same as the event horizon in the classical picture, so from a distance, it would look and behave exactly like a black hole from general relativity. However, up close, everything changes. The information of the matter that falls in is not destroyed. It is stored in the unique vibrational patterns of the strings that make up the fuzzball's surface. As the object radiates energy, this information can be slowly and perfectly released, thus solving the information paradox in a beautifully complete way. Fact 98. A century of understanding. Our journey to understand black holes is a testament to the power of human curiosity and ingenuity, a story that has unfolded over the last century. It began as a mathematical curiosity in 1915, a strange solution to Albert Einstein's equations of general relativity that even he found unsettling. For 50 years, they remained little more than a theoretical abstraction. Then, in the 1960s, the term black hole was coined, and the discovery of quasars and pulsars made the idea of superdense objects a physical reality. The 1970s brought the first strong candidate, Cygnus X1, and Stephen Hawking's revolutionary work on their quantum nature. For decades, our evidence remained indirect, but the pace of discovery accelerated dramatically in the 21st century. In 2015, LIGO felt the direct vibrations of space-time from two black holes merging, allowing us to hear the cosmos. And in 2019, the Event Horizon Telescope delivered the final, definitive proof, allowing us to see the shadow of the abyss itself. In just over 100 years, we have gone from a strange idea on a piece of paper to directly imaging and listening to these cosmic giants across billions of light-years. Fact 99. We are forged in their fire. It may seem that these cosmic monsters, located trillions of kilometers away, have nothing to do with our quiet existence on Earth. But the truth is that we are intimately connected to the very processes that create and define them. The atoms that make up our planet, the air we breathe, and our own bodies were not created in the Big Bang. The carbon in our cells, the oxygen in our water, and the iron in our blood were all forged in the hearts of massive stars. And the death of these massive stars, in the fiery blaze of a supernova, is the very same event that gives birth to stellar mass black holes. These explosions are what seeded the galaxy with the heavy elements necessary for life. Furthermore, even heavier elements, like the gold and platinum in our jewelry, are thought to be created in the cataclysmic mergers of black holes with neutron stars. So, as you look up at the night sky, remember that the story of black holes is also our story. We are the legacy of the same stellar life and death cycles that create these gravitational ghosts. The universe's most destructive forces are also its most creative. Fact 100. A symbol of our quest. In the end, what is a black hole? It is more than just a massive object. It is a symbol of the ultimate frontier. It is the physical embodiment of the boundary between the known and the unknown. A black hole is a place where our most successful theories, general relativity and quantum mechanics, are pushed to their breaking points and fail to agree. It is a cosmic laboratory where the nature of space, time, and information itself is tested in the most extreme way imaginable. For humanity, the quest to understand them represents the very best of our scientific spirit. To gaze into the deepest, darkest mystery we can find and not turn away in fear, but to look closer, to question, to calculate, and to imagine. The journey to the event horizon is a journey to the edge of our own understanding. And like any great frontier, it does not offer easy answers, but instead promises an infinity of even more profound and beautiful questions that will continue to guide our exploration of the cosmos for centuries to come.